All right, previously on concepts, or in concepts is what I guess I went with. Wow. We've been talking a little bit about circuits. And so we had left off with kind of being able to represent a circuit, and the circuit that we're representing has got a battery, has a resistor, and we have the capacity to measure current and voltage, or voltage difference, or potential difference. All of those, again, equivalent terms. And so we want to know kind of is how the circuit behaves. So we've got a couple things we can change. We can change the size of our battery. That changes the kind of overall potential in our circuit. We can change the resistor that we've put in this thing. I guess I can label these so that we can look at them. And then I can look and ask, well, if a battery is a voltage source, and a battery is a voltage source, what happens if I change the voltage? So I can ask, basically what happens to the current? Or I can ask if I hold the battery constant and I change the resistor, what happens to the current? I don't have much of a current source, so they're all outdated. Anyway, let's focus on how this current circuit behaves. So I'm going to change the voltage and measure the current. If I do that, I'm going to get a nice little graph like this, and I seem to see a trend here. I seem to see, more voltage, more current. I have chosen to graph it in this weird way. Usually you would think, if I'm changing the voltage, that should probably be on my x-axis, my horizontal axis. And it should be. But this relationship we see here, this appears to be a nice linear relationship, right? So this slope probably has some significance. It seems to relate, how much voltage we see across something based on the current flowing through it. And this relationship we're going to summarize as Ohm's law. Ohm's law tells us that the change in voltage for a circuit element with resistance R is going to look like the current in that resistor times its resistance. And so R here is this resistance. It's measured in ohms. And so if I go back up to this graph, I graphed delta V, strictly speaking, as a function of I. So this slope is going to be the resistance. Well, that's nice. And that's kind of what we expect. We need to be able to think of what it means to see a relationship like this, right? This implies there's a linear relationship between V and I, because I can graph it, and delta V equals something times I. Now, we can use this to start talking about circuits in a much more quantitative way. We can ask what current is flowing in a resistor of a given resistance. I can ask, if I need a given current in a resistor, what size battery do I need? And even better, we can start talking about more complicated circuits. So let's look at some more complicated circuits. Like this. This is what we're going to think of as a series circuit. It's going to be series because we can think of it as an AND thing. So right now I have a battery, 2 light bulbs, and in order to go through this circuit, I must go through bulb 1 and bulb 2. That AND is what tells us they're in series. I don't have any choice. There's no option. I have to go through both to get around. Now, if we were to make this circuit, and we might just make this circuit in class, we would see that these bulbs, they're going to be dimmer than if they were hooked individually to a battery. So if I had a 1 bulb circuit, like this bulb is going to be all nice and bright. Whereas if I made a 2 bulb circuit, like this, where the bulbs are, again, in series, these are going to be significantly dimmer. There are fewer and smaller squiggles, so they're dimmer. It's definitely how squiggles work. Now, if there's less brightness, that means there's less energy. That kind of is hopefully an intuitive thing, but that's how we're going to interpret that for a given light bulb, at least. And so, if there's still only 1 loop, there's only 1 current. So, if we look at this, there's 1 current flowing through this thing at all points. Now, we can ask, did that current get bigger or smaller? Well, if there's less energy being delivered, if I got the same battery, and each bulb is seeing less energy, I'm going to have to say, looking back at this kind of idea, right? That less energy, same resistance, means less current. So, if I've added 2 bulbs in series, this is more resistance than just 1 bulb. Because of that, I get less current out of this battery. There's less current flowing in this circuit. So these relationships are things that we want to try to wrap our head around. Just like when we were talking about kind of position, velocity, time, all of these things. It's a different set of relationships, but all tied together again. Now, there's one other way we can kind of complicate circuits, and that's to make a parallel circuit. So these 2 bulbs, I'm going to say are in parallel because I can go through bulb 1 and make a complete loop around this circuit, or I can go through bulb 2 and make a complete loop around this circuit. And now, if we were to make this circuit, you would see these bulbs are just as bright as when connected individually. It's almost as though the 2 bulbs, they don't see the other bulb at all. So that means the same energy is being delivered to each as when connected alone. But the battery sees this. The battery is going to run out faster, because if both of these bulbs are getting the same amount of energy, that means that battery has to be pumping out twice as much current. Because, again, coming back to this relationship, Ohm's law, if they have the same voltage and the same resistance, that means they each have to have the same current. But if we think about this back in the day, if this means there is a current chugging on through here, some current I1, and there's a current chugging on through here, some I2, what happens when these 2 currents, I1 and I2, make it to this totally connected corner? Well, every electron that's leaving these bulbs has to wind up here in this combined current, the one that's passing through the battery. And so I3 has to equal I1 plus I2. So this is just, it kind of follows from our model of this, that if these 2 currents come together or they split, they still have to add up. We can't get rid of charge in any significant way. We have to kind of obey a conservation law there. And so this means that the battery, we have to be putting twice as much charge through the battery, twice as much current through the battery in any time. Now again, the battery is not spitting out current. Remember, when we looked at the slide, the battery was not spitting out penguins. It's just responsible for supplying those penguins and moving those penguins along. If the battery has to put out twice as many penguins every second, and wow, that metaphor just got confused and weird. The battery has to put out twice as many electrons every second. It's doing twice as much work. And so we can talk about this by talking about power, is how we're going to quantify this. And power is the rate at which energy is delivered. So power is energy per time. And so what you would say is, in this case, what we're going to say that the energy that we're talking about is electric potential energy. So the energy that we want to think about is this electric potential, which we mentioned briefly, per time. Now, when we briefly mentioned the electric potential energy, we were talking about it in the context of electric potential. So electric potential, and electric potential energy. So the potential is the potential energy per charge, which means that the potential energy is Q, our charge, times the potential. So if I take this right back over to my definition of power, I can drop it right in here. And why am I doing this? Because I have a point that I'm trying to get to. And that point, once I group this Q over delta T together, Q over delta T is our current by definition. So the power delivered to a circuit is the current times the voltage. This is the power delivered either by a battery or to a circuit element. So the power, this, for example, would, if I had a resistor, this would be the voltage of the resistor. Or it could be, if it were a light bulb, the voltage of the light bulb. Or it could be, if I'm supplying it, the voltage of the battery. And in any case, it's the current flowing through that element times the potential of that element is the rate at which power is delivered to that element. Now, the unit of power is the watt. Watt, you ask? Well, a watt is a joule per second. And you may have actually heard this before, either in terrible puns or if someone's talking about their energy, their electric bill. We often talk about energy, the amount of energy consumed, in being measured in kilowatt hours. So kilowatt is a unit of power, energy per time, hour, a unit of time. So a kilowatt hour is a unit of energy. So you can look at your electric bill at home, if you ask your parents nicely, and it'll probably say that there's a rate for energy consumption in kilowatt hours and a amount of consumption in kilowatt hours. So anyway, long story short, this is a way we can talk about how much energy, or rather the rate at which energy is being consumed or generated in a circuit. And we can put it in the context of the potential across a circuit element or the current in that circuit element. And we can talk about the potential and current in a circuit element if we think of it as a resistor, and we talk about it in terms of Ohm's law. So these are the tools that we're going to use to start analyzing circuits a little more. Ohm's law, this idea of thinking about things as being in series, where we're increasing the resistance by adding more bulbs or more resistors, because we're decreasing the current, or thinking of things in parallel, where we are decreasing the resistance because we are increasing the current. We get more current out of this battery. Right. Hopefully this is good to get you started. This is mostly looking at section 16.4, 5, and 6 in your book, by the way. Have fun.